Good afternoon, everybody. Can we settle down? The last rows, are you able to hear me clearly? It's okay? The volume is okay? Yes? No? Super. So, my name is Anjan. I'm this guy over here. I will be your lecturer for this week and the next week, teaching you Verilog. Frank will be back tomorrow. He will teach sequential circuits, but today will be how to implement combinational circuits in Verilog. Do you ask a lot of questions? Do you want to use this for fun? No? Let's see. I've never tried it. It's fun. I see people throwing it around, but good. Okay. So since the classroom is way bigger than we expected last year, it's better if people kind of reduce their tone when they discuss with their partners if you want, because even if one person talks, then it kind of comes down very slowly. So let's go. What did you learn in the first 2 weeks of this lecture? Can someone close the door, please? Thank you. We saw how the history. Yeah, sure. Oh, perfect. Let's see. It's good? Perfect. So, till now, you saw the history of computer architecture, how microprocessors have evolved over the couple of decades. Last week, you saw how transistors are made and how to design logic circuits like a simple logic gate like AND or OR using these transistors. You also saw how you can put together a number of these logic gates to make something meaningful. And what you will eventually do over the course of this semester will be putting all these useful blocks into a whole microprocessor. This is pretty much what you are going to do in your lab. It's going to be very interesting, and this is one of those labs where you will actually learn how to start off from a schematic till all the way up designing your own microprocessor, writing your own code, and actually seeing it run. I believe you had a brief demonstration last week, and it was just the beginning. You will be actually playing Snake with the boards that you will be getting. You will be programming Snake. So we go from transistor level, building some logic gates, some useful blocks, putting it together to make a microprocessor, writing assembly programming for your own microprocessor, and then taking it all the way to actually interfacing a display such that you can actually play Snake, for example. And this you will be doing in groups of 2. So it's going to be a great experience. So we saw something about, so you saw how transistors are put together into a logic gate, and then these become a schematic. I don't know whether you have already done one lab. Have you? Yes. You do. So some groups have done one lab, I guess. Okay. So you will be designing kind of a schematic in your first lab, and you're not going to do something like this. Don't get scared, okay? So this is how typical boards look like. This is like one of those very old development boards. If you see, the date is 86, 87 here. So this is how schematics were done in the past. But today's microprocessors are extremely complicated. You cannot, it's not imaginable to sit and do such a circuitry in a software and trying to make it all work and put it into a chip. So what we have is our hardware description languages. And I believe some portion of it was covered last week, but just for a recap, I will continue from here. So what are hardware description languages? If I'm going very fast, let me know. If I'm going very slow, let me know. It's all going to be fine. So what are hardware description languages? They are very similar to C and other programming languages that you are more familiar. So what do? They help us, they enable us to have a very easy way of putting in these schematics such that the computers can understand and actually build these circuitries. Imagine that you don't have a programming language today. You will be writing zeros and ones. This is exactly what you can think of as these hardware description languages. They basically enable you to model the circuits in a very C-like or programming language in a very syntactic and semantic way. They support all kinds of logic gates. All the functions that you saw, like AND, OR, all these things you can simply put in it and it will realize this AND gate for you. You don't have to do anything. You simply write statements or code. So basically it's a convenient way of drawing schematics. Some other advantages of using a hardware description language is that they are standardized. It's like C. You learn the syntax and everybody can understand. It's not the same for schematics. If you see one person's schematic, this is not exactly the same as another person is going to draw the same schematic. You will actually observe this in your own labs where you will be drawing a schematic of a particular circuit, and the same circuit schematic, if you look at another group, completely different. And potentially you're not going to understand each other so well. And this is pretty much why everybody came together and developed this hardware description languages. It's not proprietary, and example, your schematics that you draw in a particular software can only be processed by that particular software. And here, you can write using a text, using a notepad, text pad, whatever you use it, and then simply feed it, and any compiler that is capable of handling these HTLs can actually process it. Again, it's easier for computers to understand what you are trying to tell, because if you draw a schematic, it's much more difficult for it to come off, somehow look at the image and process it. Instead, if you give them code, it's much easier. And also, there were several additional benefits that were discovered. So in your lab, you will actually write, so you design the circuitry, and then you have to test whether it works. What happened is that by actually enabling the schematic to be represented in such a way, we were able to actually run our own test benches and actually test the circuitry even before we go into the hardware chip manufacturing. This is very important. There's a big difference between software development and hardware and chip design, because it takes approximately 6 to 8 months from your chip design for you to get back the actual chip. But in software, you write code, you deploy it, you test, it doesn't work, and then it comes back, and then you fix the bug. But here, the turnaround time is much longer, and imagine if every bug needs to be fixed in this way, you're not going to get any product out at all. So you can actually simulate, synthesize, and test your circuitry because of these hardware description languages. There are two hardware description languages, Verilog and VHDL. Don't ask me why Verilog is more popular in the US. It is popular in the US. And VHDL is somehow the history says, somehow in the history, Europe adopted VHDL more predominantly. And in this course, we will use Verilog, and this is what I will going to be talking about this week in the next couple of hours. I would like to stress here one thing. If you follow the second edition of the digital book, it's System Verilog. We are not going to do that. Follow the first edition of the Sam and Harris book. It's actually the real Verilog. We are not going to talk System Verilog in this course. We are only going to focus on Verilog. So don't follow the second edition. There might be additional constructs, additional syntaxes, which might confuse you. Follow the first edition. So let's get started. So first thing is a module. What is a module? It's the building block of Verilog. And you can relate to this module as something meaningful, something like putting together a bunch of AND and OR gates. You can say this module is representing some behavior of a circuit that you want. And if you want to represent the Verilog module, what do you need? What do you need for a circuit? So if I show you some block like this, A, B, C, and Y, what do you get from this? Yeah? Yeah, so what you need is basically it's a set of inputs, a set of outputs, in this case only one, and then you have a whole bunch of functionality that goes into the module itself. But just from this figure, you don't know which is input and which is output. It's the exact same case even for the computer. It doesn't know what is the input and what is the output. We just know because we typically think the left side is input and the right side is output. So basically what you need to declare a module is input, output, and the functionality. And this is exactly the syntax here. So what you do when you define a module, and this is the main building block when you start writing Verilog. You write module, and all the keywords that you cannot change are in bold here, and everything else is up to you. You can even say ha ha hoo hoo boo boo, doesn't matter. Okay? But the ones in bold are keywords you cannot change. So you say module, and then you give a name for your module, which is the name for this Verilog module. It can be example, and then you can give in all the signals that are going into the module and are outputs of the module. You don't have to worry at this stage what happens inside the module. All you need to know are what are all the signals that are required to build the module, inputs and outputs. So you simply give A, B, C, Y. And then you actually tell the system what is input and what is output. And you have input, so you can say that A, B, C are inputs, exactly like this, input, 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 and then Y is an output. And then you have an end module. Note that a lot of people make this mistake in the labs. They give a space here. There's no space between end modules. So it's a very silly mistake. Just keep in mind that you don't end up with a space there. And then you give the circuit description itself inside this. We will now slowly, over the course of this lecture, we will build how do we come there. Also, one of the interesting things of Verilog is that you can write in million different ways, really million different ways. There is no good way of doing it. For example, you can write exactly the same thing like the one that we say module, test. So the name of the module is test, which we give. And then you give inputs A, B, and the output Y. Or you can actually move input A right into the braces when you declare as input A, input B, output Y, and you're still going to be fine. So there's literally no difference between writing it this way or this way. So now these A, B, and Y are basically single bit lines. So Verilog also helps you to define a bus. You already know what a bus is, right? No. A bus is a set of digital lines, okay? So it's basically, typically you don't have, you can consider a bus to carry information from one point to the other in a circuitry. And you can also, and you have multiple, so you have A, it's a 32-bit data. So you have 32 lines for the variable A. It's basically, in programming languages, you can think of it as an array. And so why do you need it? Is because, for example, when you do any kind of arithmetic, so any kind of computation, for example, a simple add, and when you do A plus B, A is going to be a 32-bit number, B is going to be another 32-bit number. Because, as you know, if you have 2 bits, you can only represent 0, 1, 2, and 3. And if you have 32 bits, you represent 2 power 32, right? So typically, for any reasonable computation, you have typically 8 bits or 16 bits or 32 bits. So you add two 32-bit numbers. And you can actually define these as the following. So you have a start and an end, which is 31. So this is 32-bit. A is now 32-bit value. So you say input 31:0. Always, it's a good practice to put the higher number in the front. It's because we follow little endian. And this little endian is basically telling you that the left side wire is the most significant bit. If something is Greek and Latin for you, please tell me, okay? Because I'm just trying to get a feel of how much you know. So you all know what's the most significant bit, right? Yeah? Okay, so you have two different ways of representing data, like digital data. So you have, if you have a 32-bit number, you can represent it in two ways. I have to write it down somewhere, and I hope everybody can see. This is a better place, or you want me to use this one, the middle one? The middle? So, you have, let's say you have 4-bit data, and I can write it as 1011. Now, if I don't tell you whether it's a little endian or a big endian, you will not know which is the least significant bit and which is the most significant bit. Why does it matter? Because in a typical system, in a little endian system, this is the least significant bit. What this means is that, and this is the most significant bit. So what this basically means is that you read this as, let's say, this is what? Quick, anybody? 1011, what's it in decimal? Yeah? 11. It's decimal 11 in little endian. But if you say big endian, then you have to read it as the other way around. So this becomes your MSB, which basically means you will say 1101. And this will, so you basically start from here, 1101. And this is big endian format, which basically means that this is going to be 13. So you see the difference. And it doesn't, So it's a good practice to always follow one particular way of telling the system. It doesn't matter when you are the only one designing the whole system. But when you're going to ask somebody to interface with your system, then it's going to be a big confusion here. All the bits are going to be reversed because the other person is going to say 0 to 31 maybe, or you are writing as 0 to 31 and the other person follows 31 to 0, and when you connect your two devices together, all your bits are going to be going exactly in the other way and interpreting it in the other way. So it's always good to follow one particular way of writing. So I strongly recommend following this little endian way of doing it. So it's like you always start with the higher order bit. Any questions here? So, some simple basic syntax. Verilog is case sensitive. You all know what it means. Some name doesn't mean the smaller order some name. You cannot start your variable names with a number, and typically white space is all ignored. And these are some recommended good practices which you can follow in your lab exercises. Consistent naming style, always use the functionality. So, aha, uhu is allowed, but it's not going to tell anything. So always use a name that is relevant to the functionality. Oops. As I said, always try using A31 to 0 and not A0 to 31. It's for maintaining little endian, which is more popular. Also, define one module per file. So the module syntax that I gave you, open a file, name the file name exactly the same as the module name. So if you say module and whose name is example, name the file example.v. And this is easy for you to find where each module is. And do not put too many modules in one single file, because it's going to be a management, it's more of a file management issue than correctness. It's going to be correct still. And as I said, use the file name that equals the module name. So there are two main types or main styles of writing hardware description languages. One is the structural type, and the other is behavioral. In a structural, what you're going to say is, you know how the circuit looks like. You know the gate level circuitry, you know how to connect which gate to which gate, or you know how each module is going to be connected with other module. So you kind of straight away represent the circuit in a structural format. The other one is behavioral, where you know that if A is 1, then B has to do something. And you can actually say this without knowing how to realize the circuitry in the digital sense. And we will see how we do both structural and behavioral, because you need both these, because when you implement and test a practical circuit, you are going to use a combination of structural and behavioral styles of writing a hardware description language. So what is structural? Let's take this simple example. In this example, you have 3 blocks. Do I see 3 blocks or 2 blocks? 3 blocks. One is called the top. Let's say 3 modules. Okay, let's say 3 blocks for now. So it's like top, small, and small. Small and top are the 2 modules. So as you can see, this is kind of, you have a bunch of input signals, A, select, C, and you have an output signal, Y. And you know exactly how you are going to connect this small module with this small module, and how the output of the first small module is going to be connected directly to the input as an input to the other small. So you know the structure of the circuitry, and you can actually directly state this in your hardware description language. And how would you do that? Let's see now. Okay, actually, let's do it together. It's easier that way. So, as you can see, you have 2 small modules, right? And what we will actually have is, you just need to write 1 small module, and then you instantiate the same small module 2 times. So you have I first and I2. And then you put these 2 instantiations into a bigger module called top. And this is exactly what is here. So you first write a top module, which you forget about the inside ones, okay? You just simply forget these small modules. All you need to see is only the top module. And for the top module, what you have? You have the inputs A, select, C, and output Y. And this is pretty much what you have here. A, select, C, Y, input A, select, C, output Y. And you have a wire, and this wire is needed to connect the block inside. I'll come to it later. Now when you consider the other module, the small module, so you have another module here, which is like module, small, and for this small module, what are the inputs and the outputs? It's A, B, and Y. And this is exactly what you write here. So you have module small, A, B, and Y. And remember, you can actually have the same name, same variable name in both. It doesn't matter. They are typically independent modules. So they will not going to complain at all. And you say which is the input, which is the output, and then you have the description of the small. What does that small do? Any doubts till now? All clear? Good. So, exactly, top, this is the top, small module, the 2 small modules. And then you have the wire, which basically connects the two small modules. There is wire and register, which people typically get confused a lot. What you need to understand for the combinational part of the course is wire. So wire creates combinational logic. And when we talk about sequential circuits next week, or in fact tomorrow, when Frank talks sequential circuits, you will really understand the difference between wire and register. But for now, let's say wire is simply a connection between 2 points. Now, what you do is now we have to instantiate this small module into the top module. So what you do is you instantiate small once, small, so you call the module name by this original name, and then you say I first, which is the name of the module itself. Sorry. And this is a name of the module. You can give anything you want, so it doesn't matter. But what is important is that you have to instantiate the module with the exact name that you gave for the module here. So the first letter is going to be small, the instantiation name, and then you start connecting wires. So what you're going to tell by this statement is that you are connecting the A port of the small module with the A port of the top module. And this is exactly what it says here. Okay? And it's now what you're going to do here is you're going to connect the B port of the small module with the select of the top module. So whatever goes inside the braces is part of the top module here. Okay? Any doubts? Sounds complicated? Very easy, right? So, and same goes for the N1 and Y as well. And then we instantiate the second small module. And you give the name I2, small I2. And then for this, what's going to happen is A is going to be connected with the wire N1. B is going to be connected with the C input. And the Y output is going to be connected with the Y output of the top module. Extremely simple. That's about it. You can also make it even more easier. You simply say small, I first, A, cell, N1. However, when you write something like this, which is when you write this kind of instantiation without the dots and the braces, you have to remember to keep the order. So the order in which you are telling these wires, so A, select, and N1, has to be exactly the same order in which the module is written. So that A will get connected to A, select will get connected to B, and N1 directly to Y. So both of them are correct. This is a safer choice because you don't have to remember the order. That's about it. Both will work perfectly fine. So from here, how does the system know what is the circuitry to actually detect? And what this process of converting a hardware description language into a digital circuitry is called synthesis. And tools that you are going to use for the labs will actually do it for you. As soon as you write such a Verilog code, and when you synthesize the code, you will end up with a digital circuitry that the compiler, or what we call a synthesizer, actually parses your code and determines what logic gate to realize and how it has to be connected. And this is the most common way of doing digital design. They do also some optimizations. I will show you one such optimization in a couple of slides. And this is also, at the same time, you can also now feed in some test inputs and simulate the behavior of your circuitry. Of course, you cannot assume that the generated digital circuit that the synthesizer generates is going to be the most optimal solution. But in general, I mean, majority of times you're going to get a very optimized circuitry, but if you are going to look for some very advanced manipulations, like you want to optimize for some power, you want to reduce gate count and things like that, you have to be very careful how you write the Verilog. But these are advanced, so you don't have to worry about it right now. So Let's kind of walk through one simple example. So you have an example block, example module. I keep forgetting that you cannot do this. So interesting. Not the best way to clean a board clearly, you see. I'm very terrible in cleaning, clearly. So let's walk through this. So you have example A, B, C, and Y. So these are the signals, and let's try to draw it. So walk me through. You have inputs A, B, and C. Let's mark it very clearly. And then you have output Y, right? And then comes, you assign Y to be, are you familiar with this representation? No. Okay. So this means not. You just invert the bit. The AND symbol out there is basically an AND gate. So you realize, and this is A and B. And you know how an AND gate works, right? Yeah. So you have, let me just, 0, 0, you get a 0 output. If you have any of them 0, you get 0, and if both of them are 1, you get a 1. So this is pretty much what we are going to do there. And let's see how we are going to, what is that circuitry? So you have not A, not B. And then you also have a not C. And then, oh, this is getting complicated. Let me simplify it. So, sorry? Exactly. But I wanted to simplify it. You simplified it for me. Anyway. So, it's not the best way to do it. You also know about the reductions, right? So let me just write it down like A prime, B prime, C prime. And you have an R. And then you have A. Can you help me? B prime, C prime. And what's the last one? I cannot see it. A, B prime, C. Right? Hopefully. Yeah. So now, how do you reduce this? You can say, you can take out A plus A, and then you can say B prime, C prime. So I basically take this, and then I simply write, take out B prime, C prime fully outside, and then I'm A prime plus A. And you know that A prime plus A is what? 1, exactly. So I don't need to worry about it. And then I can simply have A, B prime, C. And when you further take it, I can actually reuse this parameter. So what will now happen here is B prime, C prime plus A, B prime, C prime plus A, B prime, C. So now I can again take out A, B prime, and then I'm left with C plus C prime, and this goes away. So basically what's left is B prime, C prime plus A, B prime. Any doubts here? It's okay? Good. So basically this is what we want, right? But if we had done this manually, you would have ended up with several AND gates. Yeah. You will see it in the next. So in the next slide, so it's not a. So you basically end up with B prime C prime plus AB prime. Can I? And you give it to the synthesizer, it automatically gives you this. So you don't have to do the optimization for getting this circuitry. The synthesizer does it for you automatically. If you had done it manually, you would have ended up with just like how I started, lost. Right? I was totally lost. But then now the synthesizer automatically will give you this. And once you get such a circuitry, you can actually pass test benches. You will also do this in your lab exercises, where you will be able to send test signals and actually mark and see how the inputs change whenever the how the outputs change whenever the input changes. You will actually be doing this. So bitwise operators. So you can do a lot of. So you can represent AND, OR, XOR, NAND, and NOR in Verilog straight away, just like how you would do in any other programming language. You have, so as I said, the single ampersand represents AND, or the caret symbol represents an XOR, and then you can actually say an AND, and then you invert it for a NAND, and same thing with an OR. It's pretty standard, so I'm not going to run you through this. And when you synthesize this code, you're going to end up with this automatically. And if you notice, there are also buses here. So here, now the input and the outputs are all 4 bits. So you see both A and B are 4-bit input signals, and the output signals Y1, Y2, Y3, Y4, Y5 are also 4-bit signals. And there is reduction operator. For example, when you have an 8-bit A, and you want to do an AND of every bit. For example, you have A of 7, AND it with A of 6, AND it with A of 5, so on. Instead of doing every bit AND, you are just going to do Y equal to ampersand of A, and you will end up with exactly this functionality. It's called reduction operators. And what does it realize? It's pretty much this. You have A of 7 of 0 as a bus, and then you pretty much AND everything together to get an output. And you simply can say it in one sentence, Y equal to ampersand of A. Conditional assignments. So it's like an if and an else statement, if then else statement. And you have here a multiplexer where you have an input which is 4 bits, D0, and then D0 and D1, and then you have an input also which is the S, which is typically the select, and then you have an output. So you know how a multiplexer works, right? The last 4 slides of last week. Whoever said no? It's exactly the last 4 slides. Okay, cool. So again, I have to lift it up. Cool. So, multiplexer. This is 3 inputs, A, B, and then you have the output Y, right? And then you have a select. So, when select is 0, the output Y is going to be A. And when select is going to be 1, your output Y is going to be B. So it's basically, in simple terms, a switch, where you have either A or B, and depending on the value of S, whether it's 0 or 1, the switch is going to be connected to A or B. This is the digital equivalent of the if, then, and else statement. So as you see, you can assign, so you write assign inside the module. So you have a multiplexer module, which is two inputs. So you have D0 and D1. The A0 is now D0 and B is D1 here. And you have S and Y. So you have assign Y equal to S question mark. And question mark is the ternary operator because it operates on 3 inputs. It's very similar to C. So how do you read this? You read it as if S equal to 1, then D1, else D0. Got it? If S equal to 1, then you have D1. Exactly what I said. S equal to 1, you connect D1. And if S equal to 0, you connect D0. And that's about it. So you write it in one single assign statement. And this is exactly what happens. So you have a 4-bit D0, 4-bit D1, 1-bit S, and a 4-bit Y. And as I drew, it's pretty much the digital representation of your circuitry. Of course, you can add more conditional assignments. So you can say something like this, which is basically nested if and else. So how do you read it? Is if S of 1 equal to 1, then you say if S of 0 equal to 1, then D3, else D2. So you can actually see how this is represented in normal if and else statements. And you can add more. So you can do exactly the same thing by actually saying not just S of S equal to 1 or 0, but you can actually specify. I will come to what these things mean, but these are right now just think that it's a 2-bit binary number 1, 1. So if S equal to 1, 1, then Y equal to D3, so and similar on, and so on. I would, if you're interested, it's a nice assignment to kind of figure out how this would look in a digital circuitry. What do I mean by that? Now I saw 1-bit multiplexer. You have D0, D1, 1 select signal, and it was all fine. How this would be represented in a digital circuit, and how this would be represented in a digital circuit. I would leave that as some kind of a homework for you guys. When we meet next time, I would ask, and then we can discuss about it. Now you can take a break, and when you come back, we'll start with expression of numbers. So let's continue. So before the break, we saw how numbers are represented in kind of this format. Now what you're going to see is what does that actually mean. So you can typically express numbers in this way. You have n apostrophe, b and an xx. N is the number of bits. So if you consider this example, you have 8, which represents 8 bits. And then you have the b, which here is not simply a smaller version of this b, but it also means binary. So if you see here, you have binary, hex. If you want to represent it in hexadecimal, you have H, D for decimal, O for octal. These are the 4 different bases in which you can represent in Verilog. And then you follow it up with the number itself. The underscore does not mean anything. It just improves readability. That's it, nothing more. So you can actually remove the underscore when writing. So some examples quickly. I'm not going to walk you through all of them. I'm just going to pick 2 of it. So you have, what this means is a 4-bit binary number, 1001, and this means when stored, it's 1001. Consider this example. What this basically means is that it's a 12-bit number. H stands for hexadecimal. F, A, 3, which means that F is 1111, that's 15. A is 1010, and 3 is represented as 0011. And how the number is stored, or what's the value of the number, is exactly this. So you have 1111, 1010, 0011, and so is with octal and hexadecimal. So what we have seen so far is how structurally, how we can instantiate modules, how we can represent a structural circuit. We also learned how to write simple logic operations such as AND, NOT, XOR, and then of course the multiplexer functionality, which is basically the conditional statement. And we can also describe some constants with the number representation. But there's more. So you can actually, it also depends on why, so whenever you write a particular statement with multiple expressions, multiple operations, this is the order of precedence. So this is slightly different from typical programming languages. So you start with the not, and then the lowest precedence is the ternary operator. You know what is precedence? Yes. So it's basically, everybody knows, right? Okay, cool. So let's kind of, so as I said, Verilog has a lot of different ways of writing. You can write code in different ways in Verilog. Let's start with this example of comparing 2 numbers. And now we will walk through this example and see how many different ways you can write code for this, from the most complicated way for readability to the most short form of writing the same functionality, which literally is not so readable or not so understandable when somebody actually looks into that code. So you have an XNOR gate. An XNOR gate is not of XNOR, XR. So you have the same module definitions. My XNOR, 2 inputs A, B, output Z, and then you write inversion A XOR B. And you have an AND gate here, 2 input AND gate, A, B, output Z, simple, assign Z equals A ampersand B. So now, if you want to compare 2 numbers, what would you do? What is comparing 2 numbers? Say, I want to know whether it's both 2 numbers are equal or not. Yeah? Exactly why we have XNOR, and then you actually NAND it. So what is an XNOR gate? What is the functionality of an XNOR gate? Yeah?
It outputs 1 when the inputs are equal.
It outputs 1 when the inputs are equal. Exactly. So if you remember, XR is represented as this figure, and you have an XNOR. So this is an XNOR gate. So an XR has the truth table as follows. Let's say A, B output. When you have 0, 0, 0, 1, 1, 0, 1, 1. You're able to see the last rows? You fine? Okay. No answer means yes to me. So you have 0. So whenever there are at least 1, 1, then your output is 1 for an XOR gate. And these 2 will be 0. And it's exactly the other way around for an XNOR gate. So you have 1, 0, 0, 1 for an XNOR. What this basically tells you is that whenever both A and B are equal, you have a 1. Whenever A and B are different, you have a 0. So you can, in some sense, say XNOR determines equality. And XR determines inequality. Simple. And if you want to know exactly what XOR does, it's Y equals A prime B plus A B prime. This is the actual XOR computation. Okay? Nothing to do with this particular example, but do you see something interesting about the XOR truth table? Do you see? So you have 0, 0, 0, 0, 1, 1. Is there some other functionality that this represents? Is there some arithmetic functionality that this represents? Yeah? Exactly. It actually does bitwise addition. So you say 0, 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1 is 1, 0, which is the lowest part, so you have 0. And you will, and so you can actually, typically, when you're doing A plus B, you will pretty much be implementing an XOR. Got it? Great. So, when we compare two numbers, we need to determine equality. What this basically means is that we are going to XNOR A and B, and then say if it's going to be equal, then you have a 1, and if it's not an equal, you're going to have a 0. So the bigger picture here is input A0, A1, A2, A3, and so on. Why exactly are we doing this? Because this is something to do with the AND gate. Why are we doing this? What does this actually mean? So, what I drew here A, B, and Y. These are single bit numbers. What if I want to give a 4-bit A, a 4-bit B, and a 4-bit Y? And this is exactly what I'm trying to represent here with such a code. So you have A split into A0, A1, A2, and A3. So you have literally each bit of A XORed and each bit of B. And then you explicitly represent Y as the equal. So if it's equal, you have a 1. If it's not equal, you have a 0. And then what you do here is you have to XOR A1 with B1. You understand? So you have to do bitwise XNOR. And similarly, you will XNOR A2 with B2. And so on. And then you have B4. So you have 4 different outputs, each comparing A1, B1, A2, B2, A3, B3, and A4, B4. And each of them can be given a name, C0, C1, C2, C3. So you can somehow say these are C0, C1, C2, C3. And now, when you want to say that A is equal to B, how would you say that? You have to AND everything. So you have to say that A1, B1 are equal, and A2, B2. So A2 and B2 are equal, and A3 and B3 are equal, and A4 and B4 are equal. So you will have to AND all of them together to give you the equal output. Right? And this is pretty much what happens here. So you have XNOR modules and my AND modules. And my XNAR modules are instantiated 4 times, just like how we drew. You connect each value A0 with B0, connect it to C0, and exactly like how we drew it here. So you connect A1, B1 to C1, and so you have 4 XNAR gates. And instead of having one AND gate with the 4 inputs, you can do it 3 times, and that's it. Something that's interesting here is ha ha ho ho boo boo. What this basically means that you don't need to stick to I0, I1, I2, I3. You can give any name here. So I'm just trying to remind you here that this is important. This should match the module name that you wrote. And this can be any name that you want. And then you have the final AND. So this 3 AND representation, So this representation of 4 input, all C0, C1, C2, C3 turning into equal, you can also write it as you have C0, you have C1, and you have C2 and C3, and then you have another AND here, which is equal. So this is exactly the same circuitry. This is in using just 2 input AND gates. And this is what is represented there. Any doubts? Yeah?
Could we also use buses for that?
This is a bus. Oh yeah, sure. It's not a bus yet, but wait.
And another question, are there like primitive building blocks?
Yes, you have XORs and AND straight away. But this is more for you to kind of understand. So you can use A XOR B straight away. But there are no adders, for example. Yeah. So this is one way of achieving what you want. Another way is you don't have to write an AND module. You can directly, you can simply instantiate the XNAR and directly use C01 equal to C0 and C1. What that basically means is that I have given this as C01 and this is C23, and that's it. So I didn't write any separate module for this one. I just simply assigned C01 to C0 ampersand C1, and you don't need to instantiate AND. There's another way of doing it. What changed here? Let's try again. Yeah, so you can also do exactly what I told here. So you can simply AND everything together. Let me put it down just for comfort. So you can simply AND all the outputs together to make the equal. Or you can also use, what is this? What does that represent? It's reduction operator, exactly. We just saw it like 15 minutes ago. So instead of doing C0 and C1 ampersand C2 ampersand C3 and individual wires like how we do it, what you can do is you can actually do a bus definition here. So you can make C as a 4-bit bus. And then what we are trying to do is exactly a reduction operator. You're trying to AND every bit of the bus with itself. So you have equal to ampersand of C, and it's a short format. Of course, this affects readability, but it's just one way of showing, it's a way of showing how many different ways you can write Verilog code. And this is not the end of it. I can replace the A0, A1, A2, A3 with bus, as he mentioned, with 3.0 and 3.0. So it's both of them are 4-bit buses, and directly you can include them in your instantiations. Or you can simply do this. You don't have to individually XNAR bit by bit. You can simply say C equals A XOR B whole inverted. And what Verilog synthesizer will automatically do is it knows that C is a bus, A is a bus, B is a bus, or 4 input data. when it does this assign operation, it's going to automatically convert all the 4 bits into C. So this is it. You don't have to do anything more. Pretty much. Or you can also do this. Really short, but it affects readability. So you can simply say, if A equals to B, ternary operator. If A equals B, then 1, else 0. And the synthesizer will automatically figure out all the circuitry that we just drew. It is going to figure it out for you. Okay? I didn't start with here because then nobody will listen to me. Any questions? Yeah. You can have 4 input ANDs as well, but it's typically so you can. There are predefined libraries which you can say you can also use 4 input ANDs. This will actually realize a 4 input AND, but ops. So the one that I showed you, this is actually going to be a 4 input AND, but it depends on what are the libraries that you're going to tell the synthesizer to use. Because sometimes you can restrict it to say, okay, I don't have 4 input ANDs, and typically you will not get this circuitry. Because 2 input AND, it's how the hardware is realized, so it's much more easier to reuse 2 input ANDs. So you are typically restricted with this thing. But otherwise, if you are not restricted and you are doing circuitry with schematics, you just simply don't care. But when you implement it, you say try, because there will be questions. Okay, I'm trying to. It's a hint. There will be questions during the exam where you will be asked to draw circuitries with a restriction of using only 2 input circuitries. So you will have to realize logic gates, but your restriction would be use only 2 input AND or NAND gate. And this will be a question because you have a constraint there. Okay, what is the best way of writing Verilog? Does not exist. So it's up to you, but there are some good practices as I mentioned before. Easy to understand. And hierarchy is useful. What is hierarchy? Remember the first example of 2 small modules and a top module? In that, the small module and the top module, and where we instantiated the small module twice. So this is kind of a nice hierarchy, which helps us understand what is happening much better. One advice is try to stay closer to the hardware. Exactly kind of reflects one of the questions here, where why can't we do it with simply 4 input ANDs? And if there is a restriction that you cannot use 4 input ANDs, then you really need to make sure that the system does not generate it. So you always try to be closer to hardware and try to think in terms of hardware. It's very difficult. Something that I did not say right at the beginning, the main difference between C and Verilog are parallel execution. So whatever the code you see, especially in the combinational circuit part, they don't execute one after the other. It's hardware, and hardware is typically parallel. So all of them execute at the same time. So what do I even mean by that? It doesn't mean that, here you have C is assigned to this, and then you invert C. But both these are going to be executed in parallel. And the system will automatically figure out where to put, because it's going to continuously be computed. And it's not like in C where you pass through one sequence and then it's the next sequence. Especially in a combinational block, it's going to be parallel execution. But you will see in the tomorrow how you can actually instantiate sequential circuits. You can also use parameters. For example, you can simply have parameter width equals 8, which basically means that why do you need parameters? You don't have to, if you decide suddenly that your inputs are no longer going to be 8 bits, but 16 bits, all you need to change is the width equals 16, and it's going to reflect in the entire code. And you can pass this parameter to a module as well. Let's see how it's done. So if a parameter is not given, so if you're not passing any parameter and you do the standard instantiation of module, module name, and input-output signals, then it automatically takes the value of 8, the width. And if you pass it like hash 12, then width takes the value of 12, and you are realizing a 12-bit input D0, 12-bit input D1, and so on. And of course, there is a more verbose version of it. You would not be using this very often, but it's just good to know. Yeah. Parameter is, input is actually going to be realized in hardware. Parameter is just for your readability, convenience. You can treat it as some kind of a constant. And what is going to be important here is that if you're going to come back to this module, and you want to say, I'm going to change the 8-bit to 16 bits, then you don't have to go all the way and find every input and output signal and change 8 to 16. It's just for you to make it more convenient, and it's going to be converted right at the synthesizing part, and then it's going to be done. That's it. But input and output are actually going to be hard wires. You can also do bit manipulation. For example, you can assign part of a bus. So if this is a 16-bit bus, the long bus, and then there's an 8-bit short bus, and then you can actually assign some portions of some bits of the long bus to short bus. So you can actually pick up some bit values and then compute and assign this to the value short bus. You can also concatenate operators. For example, you can say Y is simply a concatenation of A2, A1, A0, and A0. So you will have a 4-bit Y with the values connected as the second bit of A, first bit of A, the least significant bit, and the least significant bit. So this will be the value. And you can also define multiple copies, just like this. Instead of doing X equals 4 times the same, you can also say 4 times this. So it's multiple ways of representing bits. Okay. I have a couple of slides. These are not important. I'm going to skip this because you might need some other prerequisites. Okay, so what about timing? We all know that circuitries are all going to be executed with respect to delays and timing. So one way of doing it is you can give time scale 1 nanosecond, 1 picosecond. What this basically means is that when you use a parameter like hash 5, it means the inversion operation is going to take place after 5 nanoseconds. So it's going to take, after 8 is changing, it's going to take 5 nanoseconds for Z1 to be the actual inverted output. And this is not going to be used in the synthesizer. It's only for simulation to test how fast your circuit can run. And it cannot be synthesized. It's not going to get converted into hardware. This is just to so if you have some hardware restrictions which says that I need my inverter to perform within 3 nanoseconds, then you can actually say, okay, assign this 3 nanoseconds, and then you test your circuitry and see if the output is seen after a certain time or before a certain time so that the system is stable. And it's exactly the same here, so your output is going to get assigned after 9 nanoseconds. This brings me to almost the end of this class. So we have seen a kind of a basic overview of Verilog, discussed behavioral and structural. So behavioral, how the circuit behaves with respect to if and else conditions. We also seen how to implement structure, when you know the structure of the circuit, how to implement it in Verilog. What's going to happen tomorrow and the following week is you're going to learn about sequential circuits. Here we only saw combinational circuits and basic logic gates. There was no memory involved. And there was no feedback, or there's no flip-flops. These are things that are very essential for a circuit to operate, and there were no clocks. And what is the clock doing in a circuitry? So all these kind of things you will hear from Frank tomorrow. And then the following week, I would come in and say how you will implement those sequential circuits in Verilog. And then you will learn about test benches, how you can test your Verilog code. And all this is going to be useful for you in the next 7 to 8 lab exercises, if not the whole semester. So what we taught in this week and the next week are going to last for the whole semester for the lab exercises. So if you have any doubts, perfect time to ask questions. And if you're not able to ask questions here, email the assistants, email ID, whatever you have, and they will be glad to answer it. Thank you very much.